You throw a ball at a wall, it bounces back every time. That's physics. That's the world. Except when it's not. Down where atoms dance and electrons spin, balls pass straight through walls. Particles exist in two places. Photons know what you're thinking, and a cat sits inside a box, dead and alive, until you dare to look. This isn't science fiction. This is quantum reality. The rules you learned, they're lies at the smallest scale. What happens when you measure something changes what it is. Distance means nothing. Observation creates reality. Why does the universe work like this? What does it mean when particles communicate faster than light? And how did we discover that everything we see is just probability waves collapsing into the illusion of solid ground? The year is 1801. Royal Institution, London. Thomas Young stands before two slits cut into a barrier. He fires light through them. On the screen behind, stripes appear. Not two bright spots. Stripes, interference patterns, the kind water makes when waves cross. Light is a wave. Isaac Newton was wrong. For 80 years, everyone believed Newton's corpuscular theory. Light travels as particles, he said. Tiny bullets of illumination. Young's experiment shattered that. The wave pattern proved it. Light spreads out, peaks and troughs colliding, creating zones of brightness and darkness. Universities taught Young's wave theory. Textbooks printed it. Engineers built with it. 124 years of certainty. Then, 1905 arrived. Albert Einstein published a paper on the photoelectric effect. Light hits metal. Electrons fly out, but only if the light frequency is high enough. Brightness doesn't matter. Frequency does. Einstein proposed light travels in discrete packets. Quanta, photons, particles again. Max Planck had suggested energy comes in chunks 2 years earlier. 1899. Now Einstein applied it to light itself. The scientific community resisted. Even Planck doubted. A wave, that's also a particle. Absurd. But experiments kept confirming it. By 1918, Robert Millikan's tests proved Einstein right. Light behaves as particles. Millikan hated the result. He spent a decade trying to disprove it. He couldn't. Einstein got the Nobel Prize in 1921, specifically for the photoelectric effect, not relativity. The photon existed. Now the paradox deepens. Louis de Broglie proposed in 1923 that if light waves can be particles, particles can be waves. Electrons, protons, atoms, everything has a wavelength. Calculate it with Planck's constant divided by momentum. In 1927, Clinton Davison and Lester Germer at Bell Labs fired electrons at a nickel crystal. Interference patterns appeared. Waves. George Paget Thompson did the same experiment independently at the University of Aberdeen with thin metal films. Same result. Both men shared the Nobel Prize in Physics in 1937. Particles are waves. Waves are particles. Nothing is solid anymore. If you value documented physics experiments and quantum discoveries like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from Nature Physics published in January 2025 by Brown University researchers Jia Li and colleagues on fractional excitons. And the Nobel Prize in Physics 2025, official documentation from the Royal Swedish Academy of Sciences on macroscopic quantum tunneling, both representing cutting-edge, peer-reviewed quantum research that confirms these strange phenomena at scales both impossibly small and surprisingly large. Now back to the information. The double-slit experiment returns in the 1920s. Scientists fire individual photons at the two slits, one photon at a time. No wave of light, single particles. Wait hours between each shot. The interference pattern still appears. One dot, another dot. Slowly, the stripes build. Each photon going through both slits simultaneously. Mathematically impossible, physically confirmed. Build a detector at the slits to see which path each photon takes. The interference pattern vanishes. Two bright spots appear. Particle behavior. The act of measurement changes reality. Remove the detector. The waves return. This is the observer effect. Not consciousness, just interaction. Any measurement device will do. The photon's wave function collapses into a definite state when observed. Before observation, it exists in superposition, both paths at once. Richard Feynman called this the heart of quantum mechanics in 1963 at Caltech. The only mystery, he said, nobody can explain it deeper, just describe it. In 2022, Imperial College London researchers performed the double-slit experiment in time rather than space using indium tin oxide. Published in Nature Physics, they created slits in time using femtosecond laser pulses, quadrillionths of a second. Light passing through temporal slits showed the same interference. Time and space both flex under quantum rules. 1935. Erwin Schrödinger sits in Oxford. He's furious at Niels Bohr and the Copenhagen interpretation. Quantum mechanics says particles exist in superposition until measured. Fine for atoms, not fine for cats. Schrödinger publishes a paper in Naturwissenschaften. His thought experiment: seal a cat in his steel box with a radioactive atom, a Geiger counter, a hammer, and a vial of hydrocyanic acid. If the atom decays, the counter triggers Sterau. The hammer drops, the vial breaks, the cat dies. Quantum mechanics says the atom is both decayed and not decayed until observed. Therefore, the cat is both alive and dead. Superposition at macroscopic scale. Schrödinger found this ridiculous. He wrote the experiment to show the absurdity of applying quantum rules to large objects. The irony: scientists embraced Schrödinger's cat as a teaching tool. The paradox became quantum mechanics. Most famous illustration: Schrödinger won the Nobel Prize in 1933 for his wave equation 2 years before proposing the cat paradox. He never intended the cat to validate superposition. He wanted to destroy it. Instead, researchers in 2012 proved Schrödinger cat states exist. Serge Haroche of Collège de France and David Wineland of the National Institute of Standards and Technology independently trapped photons and ions in superposed states. 2 states simultaneously confirmed. They won the Nobel Prize in Physics that year. Particles can be observed existing in both states. Not cats, yet, but building toward it. In 2019, researchers at the University of Vienna placed a 2,000 atom molecule in superposition. Published in Nature Physics, the line between quantum and classical blurs with each experiment. The year is 1935 again, March. Einstein writes a paper with Boris Podolsky and Nathan Rosen, the EPR paradox. They describe 2 particles that interact, then separate across vast distance. Measure one particle's spin. Instantly, you know the other's spin. No signal passed between them. Einstein called it spukhafte Fernwirkung, spooky action at a distance. He argued quantum mechanics must be incomplete. Hidden variables must exist. Some property baked into particles from birth determines their behavior. The correlation isn't instantaneous communication. It's pre-programmed. Like twins separated at birth still sharing DNA. Einstein believed this. Quantum mechanics was right as far as it went. But something deeper existed. Something local. Something real. Something we couldn't yet measure. Problem: Einstein was wrong. In 1964, John Stuart Bell at CERN derived an inequality. Mathematics. If hidden variables exist, correlations between particles must obey certain limits. Bell's inequality sets a maximum correlation strength for any local realistic theory. Test it. See if quantum mechanics or hidden variables win. In 1972 at UC Berkeley, Stuart Friedman and John Clauser performed the first test, published in Physical Review Letters. They used calcium atoms emitting entangled photons. Measured polarizations at different angles. Bell's inequality violated by a lot. Quantum mechanics correct. Hidden variables ruled out. Alain Aspect at the University of Paris. South improved the experiment in 1982. He switched detector settings while photons were in flight. No time for any signal to pass between them, even at light speed. Still violated Bell's inequality, published in Physical Review Letters. In 1998, Kidao Stau, Anton Zeilinger at the University of Vienna stretched entanglement across the Danube River. 600 meters, worked perfectly. In 2017, Chinese researchers using the Mauritius satellite achieved entanglement across 1,203 kilometers. Published in Science, the photons remained entangled. Measured one, the other changed instantly. No signal. No hidden variables, just correlation. Spooky action confirmed. Clauser, Aspect, and Zeilinger won the Nobel Prize in Physics in 2022 for proving quantum entanglement real. Einstein's objection failed. The universe is non-local. Measurement here affects measurement there, faster than light. Not information transfer, that still can't happen. But correlation, instant correlation across any distance. In April 2025, researchers at Technion Israel Institute of Technology discovered a new form of quantum entanglement, published in Nature. Photons entangled in nanoscale systems 1,000th the width of a hair, not by spin or polarization, by total angular momentum. First new entanglement type in over 20 years. Amit Kam and Shait Sesses led the research. The discovery opens miniaturization paths for quantum computers and communication. More strangeness. January 2025. Brown University announces fractional excitance, published in Nature. Jia Li and graduate students, Naiyuan Zhang, Ron Nguyen, Navketan Batra studied the fractional quantum Hall effect. They found particles that don't fit categories, not bosons, not fermions, Bosons share quantum states freely. Fermions follow Pauli exclusion. No two in the same state. Fractional excitons do both. Hybrid behavior. Similar to anyone's, but unique. A new class of quantum particles? Jia Li called it an entirely new frontier. Applications in quantum computation possible. Understanding fundamental physics deepens. The year is 1984. University of California, Berkeley. John Clark runs a lab studying superconductors. Michel Devoret joins as a postdoc from Paris. John Martinis arrives as a PhD student. Together, they attempt the impossible. Quantum tunneling at macroscopic scale. Tunneling happens all the time in atoms. Electrons pass through barriers they lack energy to cross. Wave function penetrates the barrier. Exponentially suppressed, but non-zero. Radioactive decay works this way. Alpha particles tunnel out of nuclei. Nuclear fusion in the sun requires tunneling. Protons overcome repulsion by tunneling through potential barriers. Leo Esseky and Ivar Giever demonstrated tunneling in semiconductors and superconductors in 1961 and 1960. Brian Josephson predicted tunneling across insulating barriers between superconductors in 1962. All three won Nobel Prizes in physics in 1973. But those experiments involved single particles or small numbers. Clark, Devoret, and Martinis wanted billions of particles tunneling together. Macroscopic quantum mechanics. They built an electrical circuit 1 centimeter wide. Two superconductors separated by a thin insulating layer. A Josephson junction, cooled to 50 millikelvin, 50 thousandths of a degree above absolute zero. In the superconductor, electrons pair up. Cooper pairs. They move together. Billions of Cooper pairs acting as a single quantum object filling the entire circuit. One collective wave function. The circuit sat in a zero voltage state. Trapped behind an energy barrier. Classically, it needs thermal energy to escape. Heat helps it climb over. The team measured escape rates as they cooled the system. Colder means less thermal energy. Escape rate should drop. It did. Until 50 millikelvin. Then it stopped dropping. Temperature went lower. Escape rate stayed constant. Thermal escape ended. Quantum tunneling began. The macroscopic object passed through the barrier without climbing over. Published in Physical Review Letters in 1985, they also demonstrated energy quantization. The system absorbed and emitted energy in discrete amounts, quanta, just like single particles, but this was a visible system, big enough to hold in your hand. Quantum mechanics at human scale. Clark, Devoret, and Martinis won the Nobel Prize in Physics on October 7, 2025. The Royal Swedish Academy of Sciences cited discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. The prize arrived 40 years after the experiments. Clark told the media during the announcement it was the surprise of his life. He never imagined Nobel recognition. The work laid foundations for modern quantum computing. Superconducting qubits used Josephson junctions. Google, IBM, Microsoft, SpinQ all build quantum processors based on these principles. Martinis himself led Google's quantum team. They demonstrated quantum supremacy in 2019 with the Sycamore processor. In December 2024, Google announced Willow, 105-qubit superconducting processor, error correction breakthrough. More qubits, reduced errors, critical milestone for practical quantum computers. 2025, designated International Year of Quantum Science and Technology by UNESCO, celebrating 100 years since quantum mechanics development. Free University Berlin announced contradictions in quantum theory and nature physics this year. Jens Eisert led international researchers studying entanglement theory versus quantum algorithm experts. Cultural gaps between fields revealed. Entangled quantum states cannot always be preserved with general quantum operations in laboratory settings. Previous assumptions challenged. The quantum world keeps surprising. October 2025. Polish physicists demonstrated that non-locality arises from quantum foundations. Published findings show particles separated in space behave as parts of a single system, not independent entities. The world is fundamentally non-local at its deepest level. November 2025. Hefei Institutes of Physical Science in China discovered a single organic molecule can induce the Kondo effect in a magnetic atom. Published research expands quantum interactions understanding. Professor Li Xiangyang led the work. Reality at quantum scale refuses classical rules. Particles tunnel through walls. Photons exist in multiple states simultaneously until measured. Entangled pairs communicate instantly across cosmic distances. Measurement creates the outcome. Observation collapses probability waves into definite states. The universe behaves probabilistically at foundation, not deterministic. Heisenberg uncertainty principle says You cannot know both position and momentum precisely. Measure one accurately, the other becomes uncertain, not measurement error. Fundamental limit of nature. Werner Heisenberg derived this in 1927 at Copenhagen. The more precisely you measure a particle's position, the less precisely you can know its momentum, and vice versa. It's not that the particle has both and we just can't see them. It genuinely doesn't have both defined simultaneously. Superposition. Multiple states at once. Decoherence explains why cats don't exhibit superposition. Interactions with environment cause quantum states to collapse into classical states. Loss of coherence. The quantum system interacts with surrounding atoms, photons, temperature fluctuations. These interactions act as continuous measurements, collapsing the wave function constantly. Large objects interact with environment too much, too many particles involved. Decoherence happens instantly. The cat never enters superposition because environmental interactions measure it continuously. But isolate a system well enough, keep interactions minimal, quantum behavior persists at larger scales. That's what Clark, Deverett, and Martinis proved. The delayed choice experiment adds another layer. John Archibald Wheeler proposed it in 1978. Decide how to measure a photon after it passes through the double slits, but before it hits the detector. Classical thinking says the photon already went through one slit or both. Your later choice shouldn't matter. Quantum mechanics disagrees. Choose to measure which slit, particle pattern appears. Choose to not measure, wave pattern appears. Your future choice affects past behavior. Experiments confirm this. First performed in 1984 by Carol Alley at University of Maryland, published in Physical Review Letters. The photon's path through the slits depends on measurement choice made after it passed through. Retrocausality, or time doesn't work how we think. Many worlds, interpretation offers escape. Hugh Everett proposed it in 1957 at Princeton. Every quantum measurement creates branching universes. All possible outcomes occur, each in a separate world. You observe one outcome because you're in that branch. The other outcomes happen in parallel universes. No wave function collapse, just branching. The cat is alive in one universe, dead in another, both real. You see one because you're in one. No paradox, just infinite universes. Most physicists reject many worlds, not because it's wrong, because it's untestable. You can't interact with other branches, can't prove they exist. Occam's razor suggests not multiplying universes unnecessarily. Pilot wave theory provides another option. Louis de Broglie proposed it in 1927. David Bohm revived it in 1952. Particles have definite positions always, but they're guided by a pilot wave. The wave goes through both slits. The particle goes through one. The wave creates interference pattern. The particle follows the wave's guidance. Deterministic, no randomness. Hidden variables, but non-local. The pilot wave connects everything instantly. Bell's inequality still violated because non-locality exists, just not randomness. Experiments can't distinguish pilot wave theory from standard quantum mechanics. They predict identical outcomes. It's an interpretation question, not a physics question. Quantum computing exploits superposition and entanglement. Classical computers use bits, 0 or 1. Quantum computers use qubits, 0 and 1 simultaneously, superposition. 2 qubits can be in 4 states at once. 3 qubits, 8 states. 10 qubits, 1024 states. 300 qubits exceed the number of atoms in the universe. Parallel computation. Test all possibilities simultaneously. Algorithms unsolvable classically become tractable. Shor's algorithm factors large numbers exponentially faster than classical methods, threatens current encryption. Grover's algorithm searches unsorted databases quadratically faster. Optimization problems benefit enormously. But decoherence kills quantum computers. Environmental interaction collapses. Superposition. Qubits become classical. Information lost. Error rates high. Researchers fight decoherence with error correction codes. Multiple physical qubits encode one logical qubit. Errors detected and corrected. But error correction requires overhead, many physical qubits per logical qubit. Google's Willow achieved breakthrough in December 2024. More qubits meant lower error rates, exponential improvement. The crossover point. Error-corrected quantum computing becomes practical. IBM, Microsoft, IonQ. Companies race toward fault-tolerant quantum computers. Applications transform chemistry, drug design, materials science. Quantum computers simulate molecular interactions from first principles. Classical computers struggle with electron correlations. Quantum computers handle them naturally. Design better catalysts, batteries, superconductors, optimize logistics, supply chains, financial portfolios. Machine learning algorithms accelerate. Quantum sensors detect minute magnetic fields. Josephson junctions measure brain activity in magnetoencephalography. ADMX experiment hunts axions as dark matter candidates using superconducting detectors. Quantum technology pervades modern research. Reality is weirder than fiction. Particles don't have properties until measured. They have probabilities. Wave functions describe all possible states. Measurement selects one. But which one is random? Fundamentally random. Not hidden variables. Not determinism. The universe rolls dice. Einstein hated this. God doesn't play dice with the universe, he said. Bohr replied, Einstein, stop telling God what to do. The dice roll 1. Experiments prove quantum mechanics correct to extraordinary precision. QED, quantum electrodynamics, predicts electron magnetic moment to 11 decimal places. Matches experiments. Most precisely tested theory in physics. No theory comes close. Quantum mechanics works. We just don't know why reality is this way. String theory suggests quantum mechanics emerges from deeper structure, vibrating strings in 11 dimensions. Different vibration patterns create different particles. The quantum world reflects underlying geometry. Loop quantum gravity proposes space itself is quantized. Smallest possible length, Planck length, 10 to the negative 35 meters. Space comes in discrete chunks. Time too. Planck time, 10 to the negative 44 seconds. Below this scale, space and time lose meaning. Quantum foam. Virtual particles pop in and out of existence. The vacuum seethes with energy. Casimir effect proves it. Two metal plates in vacuum attract each other. Virtual photons between plates restricted. More virtual photons outside. Net pressure pushes plates together, measured in 1948 by Hendrik Casimir. Quantum vacuum has structure. Empty space isn't empty. Quantum field theory unifies quantum mechanics and special relativity. Particles are excitations in underlying fields. Electron field, photon field, quark field. Fields fill all space and time. Particles are ripples in fields. Create a photon. Excite the electromagnetic field. Detect a photon. Field returns to ground state. Energy transferred. Conservation laws maintained. This framework explains particle creation and annihilation. Pair production. High-energy photon creates electron and positron. Annihilation. Electron and positron collide. Two photons emerge. Energy transforms. Quantum field theory underpins the standard model of particle physics. Higgs field gives particles mass. Discovered at CERN in 2012, Higgs boson detected, last piece of standard model confirmed. Quantum mechanics extends beyond atoms into fundamental force carriers and mass generation. Quantum biology emerges as new field. Photosynthesis uses quantum coherence. Light harvesting complexes in plants maintain superposition across molecules. Energy transfer efficiency near 100%. Quantum effects at room temperature in wet, noisy biological systems. Published research from 2010 onward. Bird navigation possibly uses quantum entanglement. Cryptochrome proteins in bird eyes contain entangled electrons. Earth's magnetic field affects entanglement. Birds sense magnetic field direction. Experiments suggest this, but debate continues. Enzyme catalysis might exploit quantum tunneling. Protons tunnel through barriers in enzyme active sites. Reaction rates accelerate. Life might harness quantum mechanics fundamentally. Not just chemistry following quantum rules. Active quantum computation in biology. Controversial, but evidence accumulates. The measurement problem remains unsolved. What counts as measurement? Does observation require consciousness? No. Interaction suffices. Photon hits detector. Entanglement with detector environment. Decoherence. Wave function effectively collapses. But where exactly? At what scale? When does superposition end and definite state begin? No clear boundary. Continuous spectrum from quantum to classical. Ongoing research attempts. Macroscopic superposition. Larger molecules. Microdiamonds. Eventually living cells. Where does quantum behavior stop? Unknown. Experiments push boundaries yearly. Objective collapse theories propose spontaneous collapse above certain mass or complexity. Penrose orchestrated objective reduction theory. Gravity causes collapse when space-time curvature reaches threshold. Untested. Speculative. But testable in principle. Experiments try detecting collapse signatures. None found yet. Wigner's friend thought experiment extended recently. 2 entangled observers each measure separate systems. From outside, both observers in superposition. But each observer experiences definite outcome. Contradiction. Experiments in 20 performed version using photons, published in Nature. Physics. Results challenge objective reality. Different observers get incompatible results. All correct within quantum mechanics. Objective facts might not exist at quantum level, just observer-dependent experiences. Quantum mechanics breaks philosophy. Realism says properties exist independent of observation. Quantum mechanics denies this. Locality says influences propagate at or below light speed. Entanglement violates this. Bell's theorem proves you can't have both realism and locality. Choose one. Most physicists discard realism. Properties don't exist before measurement, only probabilities. But non-locality remains. Instant correlations across space, not usable for communication. Can't transmit information faster than light with entanglement, because outcomes are random. You can't control which outcome occurs. Only correlations appear when comparing results afterward. Classical communication required. Light speed limit preserved for information transfer. Free will debates invoke quantum randomness. If brain uses quantum processes, decisions might be fundamentally random. Not determined, but random isn't free. It's unpredictable. Does quantum randomness in neuron firing give consciousness free will? Or does it make decisions dice rolls? Philosophy struggles. Physics describes, doesn't explain meaning. The Planck scale marks physics breakdown. Quantum effects and gravity merge. Current theory is incompatible. General relativity describes gravity as curved space-time, smooth continuous. Quantum mechanics describes discrete, jumpy, probabilistic. At Planck scale, both matter. Neither works. We need quantum gravity theory. String theory attempts it. Loop quantum gravity attempts it. Neither confirmed experimentally. Energies required exceed particle accelerators by factors of 10 to the 16th power. We can't test directly. Black holes might provide laboratory. Event horizons, where quantum effects and gravity coexist. Hawking radiation proposes black holes emit particles due to quantum effects near event horizon. Not observed yet. Too faint from stellar black holes. Might detect from primordial black holes if they exist. JWST searches. No confirmed sightings. Quantum reality fractures intuition. Common sense evolved for medium-scale objects. Throwing rocks. Hunting prey. Building shelters, not atoms, not galaxies. Evolution didn't prepare brains for quantum mechanics or relativity. We force understanding through mathematics. Equations predict experiments. Experiments confirm equations. Intuition stays confused. Schrödinger's equation works. Heisenberg uncertainty works. Bell's inequality. Violations confirmed. We accept the math. We build technology. Quantum computers. Atomic clocks. GPS satellites require relativity corrections, both special and general. Without relativistic adjustments, GPS position errors accumulate meters per day. Quantum mechanics enables transistors, lasers, LEDs, medical imaging. The physics works, even if it feels wrong. October 8th, 2025. Japanese researchers at Hiroshima University designed feasible method to detect Unruh effect. Published findings show acceleration turns quantum vacuum fluctuations into observable particles using superconducting Josephson junctions, connection to current Nobel Prize work, macroscopic quantum systems probe vacuum structure. September 2025, black hole merger detected confirming Einstein and Hawking predictions. Gravitational wave astronomy validates relativity and quantum effects at cosmic scale. LIGO and Virgo collaborations. Hundreds of detections since 2015. Each confirms curved space-time behaving exactly as equations predict. The universe is quantum at base. Everything emerges from probability waves. Particles, atoms, molecules, cells, organisms, planets, stars, galaxies. All quantum fluctuations that decohere into classical appearance. Reality is approximation, macroscopic averaging of quantum chaos, the solid ground beneath feet. Quantum processes locked into classical configuration through constant environmental interaction, the screen displaying words, atoms held together by quantum forces, electrons in superposition around nuclei until measurement localizes them. But measurements happen constantly. Light hits material, thermal fluctuations, electromagnetic interactions. Continuous decoherence creates illusion of solid, persistent objects. Nothing solid exists at bottom. Electrons are point particles. No size, zero radius. Yet they occupy space through wave function spread. Probability clouds, 90% likely within this region. Never certain. Nuclei contain protons and neutrons. Each proton contains 3 quarks. Quarks bound by gluons, strong force carriers. 8 types of gluons. Quarks and gluons never exist alone, only bound in hadrons. Free quarks forbidden by confinement. Energy to separate quarks creates new quarks. Pull hard enough on quark pair. Energy density high enough. New quark-antiquark pair materializes from vacuum. You get 2 hadrons instead of separated quarks. Asymptotic freedom. Quarks behave freely only when very close. Quantum chromodynamics describes this. confirmed experimentally, deep inelastic scattering, jets in particle colliders. QCD predicts all observations. Mass comes from Higgs field and binding energy, proton mass, mostly binding energy. Quarks inside contribute little. Gluon field energy makes up 98% of proton mass. Higgs gives quarks their mass, but most visible matter mass comes from strong force energy. Quantum field energy becomes mass through E equals mc squared. Energy and mass interconvert. Mass is condensed energy. Energy is potential mass, unified by relativity. Combined with quantum mechanics, we get quantum field theory. The framework underlying modern physics, tested to extreme precision, never failed. Standard model describes all known particles in 3 of 4 forces. Electromagnetic, weak, strong. Gravity excluded. General relativity handles gravity. Separate framework. Incompatible with quantum mechanics at fundamental level. The search for theory of everything continues. Unify all forces and particles in single quantum framework. String theory candidate, extra dimensions, supersymmetry. Unproven. Loop quantum gravity candidate, quantized spacetime, background independent, unproven. Other approaches exist, all speculative beyond current experimental reach. What we know for certain, quantum mechanics describes reality at small scales with perfect accuracy in all tested cases. Entanglement exists over any distance. Superposition exists until measurement. Measurement changes state. Tunneling happens, energy quantized. Uncertainty fundamental. Wave-particle duality confirmed. Decoherence explains classical emergence. Quantum computing works. Applications accelerating. New discoveries monthly. 2025. Nobel Prize extends quantum effects to macroscopic scale. 40-year-old experiments finally recognized the quantum revolution spreads from atoms to objects we can hold. But the deepest question remains, why? Why does the universe operate on probability? Why does measurement collapse wave functions? Why non-locality? Why quantization? Why superposition? Physics describes how math predicts outcomes. Experiments confirm predictions. But why reality chose these rules stays unknown. Maybe no. Why exists? Universe simply is quantum, no underlying reason, or maybe deeper structure awaits discovery. Extra dimensions. Hidden variables that don't violate Bell's inequality by being non-local. Multiverse, where all possibilities realize we see one branch, or consciousness somehow fundamental to collapse. Roger Penrose suggests quantum gravity in brain microtubules causes consciousness. Orchestrated objective reduction. Controversial. Most neuroscientists reject it, but untested. The measurement problem might require new physics. Beyond standard quantum mechanics, or new interpretation that makes sense of existing math without changing predictions. Consistent histories interpretation, relational quantum mechanics, transactional interpretation, cubism treating quantum states as subjective beliefs. All interpret the same mathematics differently. Predict identical experiments. Philosophy, not physics. Until testable differences emerge, we choose based on aesthetic preference. Copenhagen interpretation dominates by historical inertia. Many worlds gains adherence among younger physicists. Pilot wave theory maintains small following. Objective collapse awaits experimental signature. We built our civilization on quantum technology without understanding quantum foundations. Transistors use tunneling. Invented 1947 at Bell Labs. Integrated circuits followed. Modern computers, smartphones, internet. All quantum devices. Lasers use stimulated emission. Quantum process. Invented 1960. Applications everywhere. Optical communication. Surgery. Manufacturing, materials analysis, barcode scanners. Nuclear magnetic resonance uses quantum spin, became MRI, medical imaging revolution. Atomic clocks use quantum transitions. Define the second, power GPS satellites, international time standards. Quantum cryptography enables secure communication, quantum key distribution, eavesdropping detectable, information security transforms, and now quantum computers promise exponential speedup for specific problems, drug discovery. Artificial intelligence, optimization, cryptography breaking and making, materials design, financial modeling, climate simulation. Problems intractable classically become solvable if we achieve fault-tolerant systems. If decoherence controlled, if scaling succeeds, many ifs remain, but progress accelerates. Willow processor. In December 2024, crossed error correction threshold. Practical quantum computing approaches. In 1984, a team in Berkeley built a centimeter-sized circuit, cooled it to 50 millikelvin, watched billions of electron pairs tunnel through an energy barrier as a single quantum object. They measured quantized energy levels in macroscopic system. They demonstrated quantum mechanics applies beyond atoms. Reality is quantum at every scale we can test. We just need isolation. Decoherence hides quantum effects in everyday objects. But remove decoherence and quantum strangeness emerges even in things we can touch. Clark, Deverett, and Martinis opened the door. Quantum technology walked through. The reason quantum reality is stranger than you imagine isn't that particles behave oddly. It's that they behave exactly as mathematics predicts, and mathematics predicts impossible things. Tunneling through walls, existing in multiple states, instant communication across space, observation creating outcome. Every experiment confirms the math. Every application proves the theory. The strangest part is that it works. The universe runs on rules that make no intuitive sense, yet produce precisely accurate results. We measure electron magnetic moment to 11 decimal places. Theory matches experiment. We test Bell's inequality across continents. Quantum mechanics wins. We cool circuits to near absolute zero and watch macroscopic tunneling. Just as equations predict, reality is quantum. Reality is probabilistic. Reality is non-local. Reality is superposed until observed. These aren't philosophical statements. They're experimental facts tested thousands of times across decades by researchers worldwide using equipment built on the principles they test. The cat is out of the box, both literally and metaphorically. Schrödinger's thought experiment designed to mock quantum mechanics became its symbol. Clark, Deverett, and Martinis built a giant Schrödinger's cat, billions of particles in superposition, tunneling without thermal assistance. Energy quantized in macroscopic system. The experiment succeeded. The theory confirmed. Quantum mechanics is reality at all scales, just harder to see in big warm objects, but it's there, underneath everything. Probability waves collapsing into the world you see, the solid ground, the light in your eyes, the electricity in neurons, all quantum processes averaged into classical appearance. Scratch the surface. The quantum strangeness waits underneath. Strange but true, tested but inexplicable. That's quantum reality.